Assalamu alaikum wa rahmatullah. I am Radwan Othmani from Electrical Engineering Department, and I would like to welcome you to this series of lectures on signal theory. In this first lecture, we are going to explore an overview of what is called signal theory. But before we start, let me tell you about my objective here and my method. My objective is not to accumulate formulas, but to clarify ideas. And for this, we are not going to do long pages of equations and calculation. Instead, we are going to start with something simpler. We are going to start with questions. And by answering these questions, I hope that the formulas will then appear naturally, not as imposed techniques, but as a necessary response. So what kind of questions we are going to ask? We are going to ask natural questions that arise naturally when we encounter a new discipline. So we are, for example, going to ask, what is signal theory? More simpler yet deeper question, what is a signal? And what do we mean by theory? A more important question, why are signals important that they deserve an entire theoretical framework? And finally, how this theory is built. So our work here will resemble that of a detective. We will ask the right questions, follow the clues, and progressively uncover what signal theory is really about. So let's start with the first question. What is a signal? Instead of starting with abstract definitions that you might find in textbooks, let us begin with examples. My voice is a signal. It carries intelligible words, or at least I hope it does, and because it carries words, it carries information. Here is 1 second recording of a voice signal. You can see that it varies over time. The amplitude changes continuously, and this variation is not random. Of course, the signal itself is random, or it is classified as random signal, but the variation inside it is not random because it reflects the content of what is being said. Other kind of signals are electrocardiograms and electroencephalograms. They are also signals. They reflect respectively the activity of the heart and the brain. And you can see that they also vary over time. And from them, we can determine whether these organs are functioning normally or not. So once again, we observe a time-dependent variation, and this variation carries meaningful information. Another kind of signal, perhaps less obvious, is the image. Here are some examples: a satellite image, an MRI scan, and an aerial view of what could be a military base, or indeed it is a military base. They all contain information. Satellite image may reveal an approaching storm, or it could tell us about weather. An MRI scan may reveal a tumor. An aerial image may reveal strategic installation and very important information, sometimes under the pretext of national security. However, images do not necessarily vary over time. Instead, they vary over space. So an image can be seen as a variation of brightness or color according to the spatial coordinates x and y. So instead of a function of time, we now have a function of space, but we still have variation. Now, what happens when an image varies over time? we get a video, and a video is therefore a three-dimensional signal, so two spatial dimensions, x and y, and one time dimension, t. So it is another important type of signal. Videos, for example, from surveillance cameras or self-driving car system can reveal the presence of danger. They may detect motion, obstacles, suspicious behavior, or any sudden changes in the environment. So once again, they carry information and they vary over multiple variables. So from all these examples, we have signals from different nature, from different origins. Some are physical, some are electrical, others are simply variations of light intensity or colors. The point is this: what do all these signals have in common? So first, they all vary according to one or more variables, and second, and more importantly, they all carry information, and that is the essential point. Now, from everything we have seen, we can now propose a natural definition. A signal is a quantity that varies with respect to one or more independent variables and carries information. This information is encoded in the variation of the signal. So this last word, information, is the key to answer the next question. We study signals because we care about the information they contain. So is this sufficient to justify the development of an entire theory? No, not quite. We need a theory for signals because in most cases signals are not clear. We cannot interpret them directly. Something masks them or something distorts them, and that something is what we call noise. One very common example, one of my favorite example, consists of this. Imagine that you want to listen to your favorite radio program, but we don't have a theory for signals. So this is what you are going to listen to without a theory of signals. Sorry for the noise, but it's a very useful example. Now, the question is, how is this theory built? The short answer is that this theory is built upon a dense and highly abstract mathematical framework. We use mathematics because it allows us to do abstraction, and abstraction means the transformation of real objects into mathematical objects. Sea waves could be abstracted to or into a sine function, and an image here, a binary image, could be abstracted into or as a matrix. And by transforming real objects, which are signals, into mathematical objects, we can now measure them, transform them, operate on them. We can process them in order to extract the information. So signals, for instance, are transformed into functions of one or several variables, sometimes into vectors and matrices, depending on how we choose to represent them or depending on their nature. For example, a time-varying voltage becomes a function of time as S of t. In the other hand, operations performed on signals are written as mathematical transformations, filtering, modulation, convolution, Fourier transform, and so on. They are all mathematical operations. You are going to use integral, derivative systems, electrical systems like filters are described through differential equations. Random process are described through probability and statistics and so on. So we are going to use mathematics, but not too much, because the purpose, as I said at the beginning, is not to accumulate formulas, but to clarify ideas. So every single mathematical concept we are going to introduce, we are going to try to justify or to explain why do we need it and how it does work. So as a summary, we have in this video asks questions and give answers about what is a signal, why do we need a theory for them, and how this theory is built. That's all, and see you in the next video. Thank you very much.